Hey guys, welcome to Victory Education. This is your Narsiman, and the topic which we are going to talk about today is about the Coulomb's law. Till early 17th century, the scientist knows that the like charges has a tendency to repel and the unlike charges has a tendency to attract each other. But the scientists were not able to figure out how strong the charge is, what is the unit for that charge. You want to remember one thing, any kind of laws which we read today is not just the law which that particular scientist or physicist make, right? So it is a series of different people works on a particular thing and someone conclude with the above series. Example, when it comes to Coulomb's law, the first one who determined electric forces follows an inverse square law is by Joseph Priestley, and he determined this in the year 1767. A year later, in 1769, a Scottish scientist John Robinson states that the force of repulsion between two spheres with the charge of a same sign varied as x equal to 2.06. So after this, in year 1785, our hero of this video, Charles Austin D. Coulomb, published his first law. So the Coulomb's law states that the force of the magnitude Fe is equal to k q1 q2 by r square, which is nothing but reverse square law. The Coulomb's constant k is approximately equal to 9.0 into 10 to the power of 9 n m square c square, and q is the point charge 1, q2 is the point charge 2, and r is the distance between these two charges. Hold on here. Are we not familiar with this equation? Yes, we do. This equation is very similar to the equation of Newton's law of universal gravity, which he published on 15 July 1687. Newton's law of universal gravity states that F1 is equal to F2 is equal to G, where G is the universal gravitational constant, and M1 M2 by R square, where mass M1 is the mass of the first object, M2 is the mass of the second object, and R is the distance between them. So now let's come back to the Coulomb's law. So Coulomb's law is mostly similar to what Newton states. So according to the Coulomb's law, Fe, the magnitudinal force between two objects or two charges Q1 and Q2, is equal to K Q1 Q2 by R square. See in detail about this law. This law has a small modification when we compare the directions between them. As we know earlier, the like charges has a tendency to repel each other and the unlike charges has a tendency to attract each other. So if we're going to consider the direction of the force, then we have an R vector where the formula just gets rearranged as F equal to Ke Q1 Q2 by R square into R vector, where R vector shows the direction in which we're going to experience the force. We can identify the value of Ke, Coulomb's constant, is by 1 4 pi E naught, where E naught is the permutative value on the vacuum. So we know that E naught value is 8.85 into 10 to the power of minus 12 c square and m square. So if you're going to substitute the value for Ke, you will get the value for Ke as electrostatic constant 8.99 into 10 to the power of 9 n m square per c square. So for our easy calculation, we always consider 8.99 as 9 into 10 to the power of 9 n m square c square. This is called as a Coulomb's torsion balance. Okay, so this is just a simple experiment where he has a two spheres. One sphere is a B and another sphere is an A, and he has a value here to identify what is the torque value, how much this ball is going to repel or attract. Based on that value, he concluded that the Coulomb's law or Coulomb's value is going to be the force between these two spheres Q1 and Q2 is going to be Fe is equal to K Q1 Q2 by R square. Now let's see a couple of problems using this Coulomb's law. So this is your first problem. I would recommend you to pause the video here and read the problem and try to solve it yourself. Suppose that the point charges each with charge of 1 coulomb are separated by a distance of 1 meter. Determine the magnitude of the electric force of repulsion between them. Now let's see how we can solve this problem. On this problem, what we know is like Q1 is 1 coulomb, Q2 is 1 coulomb, and D, the distance is 1 meter. So what we don't know is the F, right? So F is equal to K into Q1 Q2 by D square. So we know the value of K is 9 into 10 to the power of 9 and M square C square, and Q1 is 1 coulomb, Q2 is 1 coulomb, and the distance between them is 1 meter square. So if you're going to solve it, you will get an answer as 9.0 into 10 to the power of 9 Newton. For an easy reference, I just made a simple example as 1 coulomb, but in a general way, 1 coulomb is a huge amount of current, right? It's a huge force. So when you're going to solve the problems, most likely you will get the problems as in microcoulomb or nanocoulomb. Remember, whenever you get a value as a microcoulomb or nanocoulomb, you need to convert them into coulomb. So let's watch an example now where you have a values in nanocoulomb. Pause this video here, try to solve this problem by yourself. If you are unable to, or if you're done with your problem, come back and play this video. Hope you try to solve this problem. Now let's read this problem. Two balloons are charged with an identical quantity. The type of charge is minus 6.25 NC nanocoulombs. They are held apart at a separation distance of 61.7 centimeter. Determine the magnitude of the electric force of repulsion between them. So let's see what are the given values. Q1 is minus 6.25 NC, Q2 is minus 6.25 NC, and the distance between them is 61.7 centimeter. Now let's convert it into coulombs and meters. So your Q1 value would be minus 6.25 into 10 to the power of minus 9. Your Q2 value would be minus 6.25 into 10 to the power of minus 9. And the distance between them would be 0.617 meter. What you have to find is the F, the force between them. So as we know, like we just going to substitute these values in our formula. F equal to K into Q1 Q2 by D square, where you have your K is 9 into 10 to the power of 9 and M square C square, and you have your Q1 is 6.25 into 10 to the power of minus 9 C, and you have your Q2 is 6.25 into 10 to the power of minus 9 C, and your D is 0.617. We always use the magnitude of the charges, so we just neglect this minus symbol. So on this case, the value is the force is going to be a repulsive force, but since force will always never have a negative or positive value, so I'm just taking a magnitude of them. So if we're going to solve this, you will get an answer as 9.23 into 10 to the power of minus 7 Newton. Hope you would have got the same answer. Hope you liked this video. Like it, share it, and subscribe it. Thanks for watching this video. Have a wonderful day.